Hello, and welcome to Backer Breaks It Down. In this episode, we are going to look at double angle identities, and we are going to use double angle identities to find exact values of trig functions. So previously in class, we derived the double angle identity for sine and cosine. So you may remember that. And if you don't, well, here they are. Okay. So we've got the double angle identity for sine as sine of 2 alpha, that's your double angle, is equal to 2 times sine of alpha cosine alpha. Tangent of a double angle, we didn't actually derive that one. Sorry, I know you're so disappointed. But tangent of a double angle can be found by calculating 2 times tangent of the angle and dividing that by 1 minus tangent squared of the angle. Now, when it comes to cosine of a double angle, there are 3 forms of it. The one that we derived in class was this one, cosine of 2 alpha is equal to cosine squared minus sine squared. Now, honestly, for these problems that we're going to do in this video, that one's the best one to use. The other 2 variations, they basically substituted in the Pythagorean identities and created 2 other ones that we can use. But for these types of problems, I would use the cosine squared minus sine squared. Okay, the other 2 we'll use more so in equations, all right, but not so much for these. All right, so these 3 problems here, it says to use a double angle identity to find the exact value for each trig function. You do want to first start by drawing a reference triangle for your angle, okay? And so they tell us that sine alpha is equal to 12 over 13, and that alpha is in between 90 and 180. Well, here's 90 degrees, here's 180 degrees, so we're in quadrant 2. So I can draw my reference angle. And we all know that sine is the ratio of the opposite over the hypotenuse. So the opposite would be 12 and the hypotenuse would be 13. And then I just use the good old Pythagorean theorem to find the missing side. So after I go and do the Pythagorean theorem and all that math, I get 5. And then as always, check your signs, S-I-G and S. Here in quadrant 2, that 5 would be negative. Okay. So when we use a double angle identity, it's a formula. We do want to substitute into the right side of the formula. And so for sine of 2 alpha, I'm going to substitute in 2 sine alpha times cosine alpha. And so when it comes to like what is sine alpha, what is cosine alpha, I'm getting that from my reference triangle. And honestly, like I already know what sine alpha is. Sine alpha is 12 over 13. Okay, cosine alpha would be the adjacent over the hypotenuse. So cosine alpha would be negative 5 over 13. So all I'm going to do is I'm going to substitute these ratios into my identity formula. Okay, and so it's going to look like this. I'm going to have 2 times 12 over 13 times negative 5 over 13. And multiplying fractions is really easy. All you have to do is multiply the numerators together and multiply the denominators together. And then if you can simplify the resulting fraction, you really should. Okay. But I didn't like write down sine and anything following it. Sine of alpha, like I said, it was given to me. Sine of alpha was 12 over 13. And cosine of alpha, that's just the ratio that comes from my reference triangle. So cosine of 2 alpha, like I mentioned earlier, I prefer this expansion of cosine squared minus sine squared. Okay, so from my reference triangle, I'm like, ooh, what is cosine alpha? And cosine is the adjacent over the hypotenuse. So negative 5 over 13. And then we have sine squared alpha. So I'm like, oh, what is sine alpha? Remember, that was like given to us as 12 over 13. And so I substitute those ratios into my formula, and then I expand it. Negative 5/13 squared is 25 over 169. 12/13 squared is 144 over 169. And then I just subtract these 2 fractions, The denominators are already the same, so that's excellent. So I'm just subtracting my numerators. That's where I'm getting negative 119, and the denominator is 169. So tangent of a double angle, this one is probably the more complex one of the three because it does involve a fraction to begin with. But I'm still just using my reference triangle, and I'm getting tangent alpha from my reference triangle. So tangent is the opposite over the adjacent, so that's where the 12 over negative 5 is coming from. So the formula says 2 tangent alpha, and I'm writing down 2 times, and then remember tangent alpha is negative 12/5. Okay, in the denominator I have 1 minus tangent squared alpha, so I got the 1 minus, and then I have to square the tangent. So tangent is negative 12/5, and I'm squaring it. So I did that math. When I went like negative 2 times negative 12 over 5, I got 24 over negative 5. In the denominator, I still had the 1 minus, and then I did square the negative 12/5, and I've got 144 over 25. So I have this complex fraction because I have these two mini fractions in a big fraction. And so I need to simplify this. And I can simplify this by multiplying all three terms by the LCD of the mini fractions. And the LCD is the lowest common denominator, and it would be 25. So that's why I'm multiplying everything by 25 here, times 25, times 25, times 25, okay? And so when I do that, when I go negative 24/5 times 25, I get negative 120. In the denominator, 25 times 1 is 25, and then 144 over 25 times 25 is 144, and then I'm just subtracting on the bottom and then simplifying the results. So really, I mean, it's a formula. That's how we want to handle it. From our reference triangles, we are getting that trig ratio. So in this case, that's where I got tangent alpha from. Now, another type of problem that you can encounter with these double angles does involve inverses. And honestly, you're essentially going to do exactly the same thing that we did in the previous three problems. We're going to draw a reference triangle in the proper quadrant. We're going to find the missing side using Pythagorean theorem, and then we're going to use our identity, the appropriate identity. So just remember, when we're working with inverses, when we see that inverse notation, if the inside of our function is positive, we're going to draw a reference triangle in quadrant 1. Now, if the inside of our function is negative and it's cosine, we're going to draw a reference triangle in quadrant 2. And for those negative insiders, for inverse sine and inverse tangent, will be in quadrant 4. Okay. So when we look at 4 and 5, like they look a little intimidating. I'm supposing that you're thinking that, but just remember, like the inverse trig function. Remember, the inverse trig function involves an angle. It's basically representing your angle. So we can think of cosine of 2 tangent inverse of negative 4/3. We can think of this as cosine of 2 alpha, okay, where inverse tangent of negative 4/3, that's alpha, okay, and that's what we would draw. That's the reference triangle we would draw to represent our angle. So this being inverse tangent of a negative, inverse tangent of a negative means that I'm drawing my reference triangle in quadrant 4. And tangent, as we all know, is the opposite over the adjacent. So 4 and 3. And here in quadrant 4, the negative would go with the y value. And then I just use Pythagorean theorem to find the missing side. So the missing side is 5. Okay, so I've got my reference triangle. So from here, it's just a matter of substituting this information into the expansion for cosine of a double angle. And so that's what I did here. Okay, so I've got my reference triangle. I basically want to find cosine of 2 theta. Cosine of 2 theta has the formula cosine squared minus sine squared. From my reference triangle, I determine cosine because that's the adjacent over the hypotenuse, so 3/5, and I'm going to square it. Sine is negative 4/5, and I'm going to square it. And that's what I'm doing in the very next step. 3/5 squared is 9/25. Negative 4/5 squared is 16/25. And then I can finally subtract. 9 minus 16 is negative 7, and this is all over 25. So number 5 can be approached the same way. Okay, you've got sine of 2 times something, an inverse something. That inverse something, well, that's your angle. All right, so basically in number 5, I'm finding sine of a double angle, and I got to draw that angle. So here we had inverse cosine of 8/17. It was positive, and everything's positive in quadrant 1, which is why I've drawn my triangle in quadrant 1. I found the missing side using Pythagorean Theorem. I basically want to find sine of a double angle. That formula is 2 sine cosine. From my reference triangle, that's where I'm getting sine. Sine is the opposite over the hypotenuse. That's where I'm getting cosine. Cosine's the adjacent over the hypotenuse. And then I'm just multiplying. 2 times 15 times 8 is 240. 17 times 17 is 289. So that's how we use these double angle identities. Basically, take the given information, draw a reference triangle in the proper quadrant, find the missing side using Pythagorean theorem, identify the ratios you need, plug them in. And that's how Backer breaks it down.